Hello everyone, this is Juan Fraire, and in this presentation I will introduce the topic toward the design of space missions with optimal accessibility via relay satellite. This talk is presented at the 6th Space Terrestrial Internetworking Workshop, or STINT, at IEEE SMACIC 2019. So, everyone knows from space networks that low-orbit satellites typically renders very short contacts with ground stations on ground. This is mainly because the orbital dynamics of low-orbit objects that has a period of orbital period in the order of 90 minutes and opportunistically visits ground stations with rendering contacts in the order of a few minutes, ranging from 5 to 7 up to 12 or a little bit more, depending on the altitude of the LEO satellite. So in general, for observation missions or general low orbit missions, there is a careful selection of orbital parameters that matches a given ground station locations, and eventually studies are actually made in order to optimally place ground stations in order to match a given mission interest. So for instance, if a mission is thought to be used for in a polar orbit. Therefore, ground station locations near the poles are typically desired. Another options to enhance the connectivity between the satellite and ground station is also to leverage existing so-called ground station networks. One option or one well-known company doing this is KSAT from Norway, and these are basically sets of ground stations intelligently spread throughout the surface. So you have ground stations on the North Pole, in the South Pole, in the equator, and throughout most of the Earth's surface that can actually be rented or used or booked in advance in order to download valuable data from low Earth satellites. And but still, sometimes it's always desired not to rely on third parties for this type of activities, and an appealing options to do this is to leverage relay satellites, self-owned and self-launched relay satellites that can be used to enhance this already short contacts with ground station from space to ground. And these relay satellites are what we are going to be focusing on this presentation. So the mission, the relay satellite mission design is not simple, and involves quite a big set of parameters, and this is extends from a traditional satellite mission of observation mission, for instance, and involves different aspects. Mission objective, for instance, which is defines which is the data generation process, how much data we're going to need to download, and which moments this is going to typically happen. If this is an imaging mission, therefore we will need to take into account at which moment this image is taken, and therefore where is the best place to locate a given relay satellite, for instance, to once this image is taken, be able to transfer it via an inter-satellite link to a relay satellite, and therefore download that image to ground. Keplerian parameters come into play, obviously, for each of the relay and also of the main satellite missions. One or many present ground station locations also come into play. The communication constraints that happen here, which is the elevation at which the communication can be established, which is the ranging from that the intersatellite linking can be used, and this also involves propagators, or to determine what's the position is going to be of the satellite in the future, and therefore calculate which is the access time, or which is the overall topology of the mission. The main complexity rises when we see that actually each of these parameters actually are multiplied n times or x times depending on the quantity of mission satellites that we are going to use, the quantity of the relay satellites that we are going to use, and the quantity of the ground stations that are going to be present in the scenario that we want to evaluate. All in all, putting all this together, access time can be calculated, and access times between the mission satellite, the relay, and the ground station is what ends up defining the quality or the value of a given mission relay-based mission design. And the access time is nothing else than a set of times, of time periods, from start time to end time, who which asset is able to communicate with which asset at any of these times. So this is analogous to what's on the late solar networking known as contact plan. So this can be used both for analyzing the network from a given scenario and calculate which is the accumulated access time or what's the frequency of the access time that you have with the which is of the assets, or this can eventually also use for scheduling, for predicting what's going to happen in the network in the future and schedule related activities or communications or book the resources in advance. But let's try to break this apart a little bit and try to classify the different access that we're going to be dealing with, so we can actually define and try to optimize what can eventually be a relay-based mission. So obviously, the most immediate classification that we can get from access periods or access time are those access which are direct access from the ground station to the mission satellite, and which are obviously happens in real time as the mission satellite is able to directly send the data that it has in memory or that it is acquiring at the contact moment to the ground station. So this is one type of contacts or one type of access that we can be dealing with in a relay-based satellite mission. Where can we go from here is to also, beside having this contact between ground station and the mission satellite, we can also have contacts at the same time between the relay satellite and the mission satellite, and the relay satellite and the ground station at the same time. These are typically, this is another possibility of communication, another topology that can be happen at any given moment. But in general, this has not a major impact, as when this type of communications is present, one generally chooses to download the data directly from the mission satellite down to the ground station and basically ignore the communication with the relay or from the mission satellite or from the ground station to the relay. An interesting alternative, another way of thinking of what type of accesses can happen simultaneously are when I have an access from the ground station to the relay, and at the same time I have an access from the relay to the mission satellite. And this is a relay case. This is a relay case when the mission satellite can deliver data to the relay and the relay deliver data to the ground on behalf of the satellite. And this also happens on real time as the relay, as soon as the data is received, the data can be immediately forwarded to the ground station. So we are on a real-time case and an indirect case in this particular case, as the mission satellite is not talking directly with the ground station, but through a relay satellite. And then to complete the possibilities of accesses, we also have direct access from the ground station to the relay only, and from the relay to or from the mission satellite only. And these cases are of no value in case of real-time access is required, but might be of value when relying on store, carry, and forward networks, which also known as delay tolerant networks. Because in this case, this type of access are still valuable because I can use inter-satellite link between the relay and the mission satellite. And then in another moment, I can exploit the access to the relay from the ground station and get the data down to ground as fast as possible. So this is a particular type of accesses that can be of interest if and only if store carry and forward data download is sought or accepted in the relay-based satellite mission. And as mentioned, these original cases where there is a simultaneous contact between ground station and the mission satellite, and also between the mission satellite and the relay, or the relay and the ground station. These are typically redundant contacts that can be just ignored, or as known as well in the optimization world as don't care, or basically, or some effect that we might want to minimize as well. That's also a possibility. So all in all, in this image, we have like what can be like a taxonomy of what are the type of accesses that occurs in missions where you have ground stations, the main satellite missions, and also relay satellites playing its role in this network. Based on this taxonomy, we can derive different cost functions. So we can characterize and measure how good or how bad are the networks that we can study, and arbitrary cost functions can be defined. This is just an example that we use in this paper. In this case, we're assuming that we do want real-time and indirect access. This is something we took care to have in this example we're talking about here, and we don't want to have store carry and forward. And this is why we have as a positive factor in cost, we are considering that ground station to relay only and mission satellite to relay only are something that is costful for us. This is something we don't want. This is adding cost to the system, and we want to minimize this effect. On the other hand, we are honoring. This is on the second row. There is a minimum symbol in the summation here, that we want that's something that reduces cost, and therefore is something that is desired in the systems. Is that when we have simultaneous overlapping contacts between ground station and relay, and ground station and mission satellite at the same time. So um, this is where we want to have like an optimal assessment here. We want to have minimize, also maximize the possibility of having a relay access to the mission satellite from the ground station. And once we have designed this cost function and also have defined what are the accesses that we can play with, we have chosen to model and analyze the system via what's called simulated annealing optimization. And simulated annealing is a combinatorial optimization that avoids to fall in local optimums by sporadically or probabilistically enabling or allowing what are called as downhill moves. This is even though I know I'm moving in a direction of my search space, as this image shows, that is basically maximizing my metric or minimizing my cost, which is the case we're talking about here. I can eventually drive away from this direction and do not follow this gradient anymore, and probabilistically accept some bad or worst metrics in order to follow alternative path that can eventually lead to a maximal and optimal, a global optimal solution. This is what's expressed in this plot we're seeing here. So what we do in our simulated annealing optimization is we model is a well-known algorithm that evolves through different stages and basically iterates on the different solutions. And for a starting data set, the solution is evaluated, is measured, the cost is measured, and once this cost is measured, there is a neighbor solution that is found. This is S4 in the image, which is a variation, a parametrical variation of the original scenario. So let's say, for instance, if we're dealing with satellite altitude, then we can variate this parameter, and then we propagate the orbit and again compute the cost of this neighbor that we have just found. And this is where in point S7 there is a decision to take, whether if we take this new variation or not. This variation is by nature random, so it can be better or it can be worse. It depends. And if it is better, it's highly likely that we can take it. If it is worse, therefore, we will likely reject it. Or with a given acceptance probability as shown on the left, we might even be able to take this solution and continue the search from this point and on, while keeping in memory, this is important though, the previous chosen solution, which is namely this is the best solution we have achieved so far. And eventually this becomes what's basically a search algorithm that seek through the solution space the best set of parameters that maximizes a given metric or minimizes a given cost function. And the parameters that we are considering, which are defined at the initial point of the algorithm, that are also redefined or modified in the neighbor definition step on S4. We basically have the ground station latitude and longitude that can be either fixed or can be expressed as a possible set of ground station locations to facilitate and diminish the quantity of places or possibilities that we can search. And then for each mission satellite and for each relay satellite we play, or we can modify semi-major axis, inclination, longitude of the ascending node, argument of periaxis, eccentricity, and so on. And each one of these parameters has a constraint, basically which is the ranges of value, and we can generate just random values within this constraint and push the algorithm to look and explore these different sets and in the expectation of finding a local or hopefully a global optima that maximizes a given cost function such as the one we showed before. A key element here is that for each iteration we will be propagating all the scenarios. So um, this is a computing expensive effort depending on the accuracy of the propagator that we are using, and many propagators typically there are some simple propagators like J2 or medium complex propagator like SGP4, or eventually high precision orbital propagators which are numerical approaches to propagation and can take quite not a despreciable amount of processing power to solve. So this is something we will try to tackle. So we want to minimize these iterations as well in order to reach a local or a global maximum. And we leverage these propagators by using the system toolkit software from AGI and combining this software via interfaces, open interfaces with the MATLAB software, where we use MATLAB to control the SDK software. So what we do is express this in a case study where we have two ground stations, one mission satellite with a defined orbit, also ground stations are defined, and we basically variate a given set of parameters from relay CubeSets. We have fixed some constraints, so same orbital circular orbit, and we also said that the phase shift between the CubeSets is also constant, so this means that the three CubeSets will be deployed in the same orbital plane, in a same orbital trajectory, but they will be separated the equal amount of angle between each of them. So the separation will be constant. Now we will play with the inclination value, the RAM value, which is similar to the longitude of the ascending node, and the argument of perigee of the orbit. So we will play with these parameters and try to minimize the cost function that we have previously shown in the upper slides. And this is a simple animation of how does this search function looks like. So we can see how SDK is being controlled by MATLAB and is basically moving these three satellites, which are equally separated from each other, from one plane to another plane, varying the inclination, varying the run angle, varying the different elements we have set to vary for this constellation. And as the algorithm searches for this, it recalculates on each iteration the metric that you are interested in, which is basically a cost function. That in this case, this cost function is expressed in percentage of time, basically. Um, so what we're saying here is that if we are around 50, we would say that the access time to the mission satellite is in the average of 50% of the time, which is um, quite a good metric actually. So considering that a typical LEO satellite can have at the very best 4 visits to the ground station of less than 10 minutes in a so this is actually quite a good metric. And this is how the metric varies, and how are the different angle parameters also vary on the animation on the right. What's interesting to see is that if we compare what's a brute force approach, where we basically swipe through all possible discretization space from the evaluated data, we get that we hit the optimal right at the end of the brute force calculation, which is in around 4,500 iterations. And this is quite a lot in terms that you need to run 4,500 propagations for the scenario that you have defined. So this is not trivial effort that you have to make. And then on the right, we have what happens with this brute force strategy when it's based in the simulated annealing solution that can reach, if you take a look, is effectively pretty much the same optimal value, the same percentage, but only at 250 iterations. So the difference is quite noticeable. These are more detailed numerics results from the difference. So this is just to mention how close the resulting simulated annealing algorithm provides a solution, a real and implementable solution through the software. And this is a plot of where are the points of the optimal value of the best of the brute force approach and the simulated annealing approach in a surface represented by the longitude of the ascending node and the inclination. And we can see that they're quite close. We're talking about the 1 or 2 degrees of separation from each other. And so it's meaning that the search algorithm is actually able to reach very good results with a drastically reduced effort of 250 iterations. And this is the resulting topology that the algorithm chooses. It's just the 3 satellites at this distance. And as you can see, the 3 satellites are practically flying. The results show that they are practically flying at the same uh, let's say perigee let's say the argument of perigee, sorry, from the mission satellite, and therefore they see the red satellites we can see here quite a lot of time. So this is where they optimize the overall time that we have to access with the ground using the 3 relay satellites. And let me insist with this is like a generic approach. Just it's worth we can change the cost function, and we can change the orbital parameters, and we can change any of the mission parameters. We can easily play and process different data and obtain the results for a given maximization or a minimization metric we are interested in getting with simulated annealing. So, as a summary, simulated annealing was proposed to support the rapid design and study of missions based on relay satellites. And case studies have shown that 58 out of 60 degrees actually is a 97% of optimality can be obtained via the simulated annealing at a dramatic reduced calculation effort of only 5.5% of the iteration. This is very important because of the, the the orbital propagation effort is quite costful, and if it's possible to be reduced or controlled, this is always an advantage. And the next step is we're already working on doing this and testing the difference with genetic algorithms. And so far, what we're seeing is that genetic algorithms outperform simulated annealing when, especially when using in larger scenarios where simulated annealing has a hard time to converge on a good solution. So genetic algorithms are already showing that they're more capable in solving this type of complex problem with so many variables and so many free uh, variables that you can choose to test the different solution space. So this is all, and thank you for your time, and please feel free to drop me a comment or an email. Thank you very much for listening.